for the opportunity to speak to all of you. I'm uh, very sorry that I'm not there live in person. I would very much have loved to be there. It would have been my first time in the Philippines. I've traveled to many places and have been in the region many times. I love Southeast Asia for many reasons, the food, the people, the sites, the history. And so I really would have enjoyed being there live, especially as it sounds like you guys are going to have a wonderful beach evening tonight, of which I'm particularly jealous. But anyway, so be it. I am speaking to you from the Jersey Shore, a different kind of waterfront situation here. And let me jump into it because I know we have not too much time. So again, I'm Mike Piech, Vice President of Business Development at Rigetti. And I'm going to talk to you about the superconducting modality of quantum computing. So just a quick intro to Rigetti. So we're a small company. We're about 150 people, of which more than a third are PhDs. So that still gives you an indication of the very research and development oriented nature of this industry. Um, so among the various modalities or ways of doing quantum computing, there are some big players who also do superconducting, such as IBM and Google, and there are a few of us smaller players who are pursuing this particular approach as well. We are one of the early practitioners of superconducting. We were founded in 2013 by Chad Rigetti, who came out of the Yale laboratory where Michel Devoret and Jay Gambetta and a number of the early founders, if you will, of the transmon particular way of building a superconducting qubit did their early work. So there's an early crowd of those folks who are spread across the industry now. Chad did himself work at IBM for a while and then founded Rigetti in 2013. And during Rigetti's dozen-year history, we have carried out a number of industry firsts. We created the first kind of quantum data center, as well as the first quantum dedicated fabrication facility. We're headquartered in Berkeley, California. And our fab is in Fremont, California, a little bit south of Berkeley. So kind of a California headquartered company, but with some offices around the world, handful of folks in London and Oxford in the UK, as well as a handful of folks closer to Southeast Asia in Australia. We also put some of the first quantum compute capabilities online in a cloud-based model. And I'll save some of the other specifics for later on. So just to put a map in front of it. So again, California-based, but good footprints in Europe and Australia as well. Unlike many particularly smaller companies out there, we have from early on really tried to combine our research and development efforts with practical real-world deployments, and really build up a notion of the engineering that it takes to make a system that not just kind of works in the hands of a couple of very brilliant PhDs in a laboratory, but rather can be brought up and made to operate with some level of reliability and performance in environments outside that very handcrafted lab situation. So the point of the slide here is just to give a sense that we have more than 20 deployments over the years around the world, many in our own data center, but some in the UK, and a number of smaller systems going live, for example, in Singapore, to give an example closer to where you all are right now. And you probably touched on this in some of the morning sessions already, but just to probably reiterate, we see three main categories or areas of use case where quantum computing in general, this isn't specific to superconducting, this is quantum computing in general, where is it going to bring value to the world, to computation, to technology, to making civilization better. And those three areas are chemistry simulation, which kind of further divides into both the sort of inorganic side, such as new materials, battery technologies, for example, or new materials that are lightweight and strong. Think carbon fiber, but whether for transportation uses, as much as we hate to always bring up military things, defense is important, so it has numerous defense applications, etc. Optimization is, as the name would imply, making things operate more efficiently, using fewer resources, less energy, etc. Canonical example, traveling salesman problem is a mathematical problem, which you can think about how to route a delivery truck, or how best to schedule airline flights, or how best to supply energy on an energy grid. It turns out that optimization really permeates so many use cases out there, and the way in which quantum computing will accelerate the optimization mathematics will bring value to numerous commercially important contexts. And then last but not least, machine learning. So there's a very interesting synergy between quantum computing and machine learning. There are ways in which machine learning can help us develop quantum faster and can help a quantum machine operate more optimally, more efficiently. Will sort of help make up for some of the noise aspects and so on. But conversely, there are ways to apply quantum computing to machine learning use cases, ways to use quantum computing to for example, train a model with a given amount of data to a higher degree of predictive accuracy, or to achieve a certain level of accuracy, to be able to do that with less training data. So there are promising directions, promising examples of how quantum could be a significant enhancement to the progress that's already happening in machine learning. Again, still talking very generally about quantum computing before even getting into specifics about superconducting. There are generally four dimensions, four characteristics or parameters of a quantum computer that are most important, and that any quantum computer vendor will give you statistics on and will talk about. The most obvious one is the qubit count, how many actual qubits are in a given quantum computer, and that pretty intuitively and obviously translates to how big of a problem the quantum computer can actually tackle. The next important one is the error rate, or its converse, one minus the error rate, being fidelity. It's well known that quantum computers in their current state of development are still subject to a lot of errors. A quantum computer is an inherently unstable physical phenomenon that is subject to a number of different kinds of distortion and interruption and interference from various just environmental sources. The third major dimension is coherence time. So this is the amount of time in which a quantum computer actually behaves quantumly, actually is able to achieve those quantum behaviors that allow it to do its unique mathematics. So things like entanglement and superposition and interference. And then last but not least, gate speed. This is the amount of time it takes to actually carry out a particular operation on a qubit. So to state what might be obvious or might be not obvious, the number of operations that a given quantum computer can actually carry out is essentially the coherence time divided by the gate speed, right? So if you have a coherence time of a microsecond, or 10 microseconds, and you have a gate speed of a nanosecond or 10 nanoseconds, then you can carry out roughly, 1,000 operations. And the number of operations that can happen in parallel, let's say 2-qubit combinations in parallel, that obviously depends on your number of qubits. So that hopefully gives a little bit of a sense of how, as a maker of quantum computers, some of the things that we are concerned with and optimizing our research and development to get better at. To kind of characterize where we and I think other vendors would more or less roughly agree with this characterization, to kind of say where we are as an industry, there's a holy grail of what's called fault tolerance, where with some amount of not just low error qubits, but with some amount of additional error correction on top of that, you get a low enough error rate where you can really carry out large computations at a scale where it's commercially relevant, where it's cheaper, it's enough less expensive and easier to do than using a classical computer that major commercial companies will buy quantum computers and start to use them for real things. We're on the way there, but we're not there yet, obviously. So many of the quantum computers that get sold today are acquired by universities and government laboratories for research and experimentation. But we, as an industry and as individual computer vendors, are every day, every month, every year making palpable progress, getting the qubit counts higher, those error rates down, and so on. So almost anybody in the industry, they'll give you different numbers in terms of how many years it will take to get there. But most practitioners out there are very confident in the progress that we're making and that we will continue to make. Okay, so now to get a little more specific about superconducting. So one thing, first of all, you've probably heard some of the different types, and you're going to, I think, hear from a couple of other speakers in the next little bit here on at least 2 different other ways of making qubits. Many of the other ways of doing qubits involve actual individual physical particles, such as atoms or molecules or electrons or photons. Superconducting is unique in that, unlike those other ways of creating a qubit, we make what's essentially an artificial quantum particle. And it's, in fact, a circuit, as we'll see in a moment. And it comprises many, many, many individual atoms and atomic particles, which, due to a particularly interesting aspect of superconducting, they act in unison. They act as if they were all together a single quantum particle, and that's what is meant by the term quasi-particle. So you have a macroscopic qubit. You have a qubit that's actually much larger than an atom or a molecule, and that is the structure that is at the heart of a superconducting qubit. A couple of the other characteristics of superconducting as a way of making qubits, and in contrast to other ways of making qubits, we have among the fastest gates out there as compared with other modalities. And in order to make a superconducting QPU, quantum processing unit, in order to make a chip that has qubits on it, the fabrication approach leverages many of the tools and process techniques that come out of the traditional semiconductor industry that makes today's chips for classical computing. And all of that together leads us to a compelling roadmap to achieving that real compelling advantage. Okay, so I'll try to take you through a quick just kind of summary of how does that circuit at the heart of a superconducting qubit actually work. So for those of you with any bit of electrical background, you may be familiar with an LC circuit, L being an inductor, C being a capacitance. If you have some energy in a circuit like that, it will naturally oscillate. The energy will just swing like a pendulum between magnetic energy in the coil and electric charge energy between the plates of the capacitor. And what we do to create a superconducting qubit is we essentially create a small LC circuit like that with one important difference, and that is that the inductor is this special construct called a Josephson junction. And it is interesting and important because at superconducting temperatures, and when one gets the energy down to a small enough level where you can go between different states, so the ground or zero state and the one state, the difference in energy between the levels is not the same. In other words, as a nonlinear induction device, the Josephson junction allows us to distinguish the jumps between different energy levels. And so what that means is we can control a qubit in isolated two-level system where we can bounce between 0 and 1 without accidentally bouncing into a 2 or 3 or higher level states that would distort our computation. So that, in a nutshell, is why that's important. So what does this look like in real life? Here's a close-up. Now, remember I said these are macroscopic structures. So unlike, let's say, the transistors on a modern semiconductor CPU, these, as we'll see in a moment, these devices are practically visible with the naked eye. The Josephson junction itself has a nanometer level scale to it, but the overall qubit structure is on the order of millimeters. So you have this construct that is laid down on a chip. And then here, as you can see, this is a blow up, but this is a square that's 5 millimeters on the side. And this shows 8 of those qubits with those Josephson junctions and other sort of structures needed to actually manipulate and operate a superconducting qubit, right? So you need drive lines so that you can send pulses in to set and initialize a state and manipulate the state of a qubit. You have readout resonators so that you can read the state of a qubit and a port to connect to. And then you have tunable couplers. That is, you have ways to couple pairs of qubits and entangle them and actually carry out gate operations, which give you the quantum computing, the universal quantum computing capability that you need to actually do quantum computing. I mentioned pulses. So superconducting qubits are controlled by microwave pulses. So if you're familiar with the block sphere representation, right? If I start with a qubit or I set a qubit into a zero state, by sending pulses with different amounts of energy in different shapes and different durations, I can I can change the state of that qubit to what I want it to be. And again, that is microwave electronics. These are pulses in the, so the qubits resonate in the 4, 5, 6 gigahertz kind of region, and you send pulses in the hundreds of megahertz regime to manipulate them, and that is carried out by electronics that are leveraging techniques that are well known in today's microwave electronics used for communications in other areas, but which are somewhat specialized for superconducting qubits. So here's an example of our latest today operating 84 qubit system, 7x12 lattice. I've mentioned tunable couplers. There are a couple other characteristics there that I won't go into. And by the end of 2025, our roadmap has us delivering more than 100 qubits, and again, cutting our error rate in half relative to the error rate that we had at the end of last year. And so what does this look like as an actual system? So that chip that I just showed you is about 1 centimeter by 2 centimeters. It goes into an enclosure, which itself then goes into a shielded region in the coldest part of a dilution refrigerator. a superconducting QPU has to operate on the order of 10 millikelvin, so extremely cold temperature to achieve superconduction. And that dilution refrigerator is on the order of 6, 7 feet, or let's say 2, 3 meters tall, and sits next to a rack of networking and classical compute equipment, as shown in the photo here. So that gives you a sense of what a superconducting setup actually looks like. I'll speed up here because I think I'm only supposed to be about 25 minutes. So an important characteristic of, or I say an important aspect of how Rigetti has gone about its business and doing its research and development is that early on we created our own fab, again, the first quantum dedicated fabrication facility. And that really has allowed us to accelerate innovation, right? To have interesting new ideas and get into a very rapid iterative test loop where we have an idea, we try it, we run an actual production, we generate chips, we put those chips in dilution refrigerators, cool them down, and then scientists can run experiments on them. And that really has allowed us to come up with a number of breakthroughs over the years. 3D signaling, for example, modular approaches where we have a QPU comprise, a composite of multiple different chiplets with inter-chiplet entanglement. I don't have time to go into the alternating bias assisted annealing, but a very interesting approach. Was there a question? Okay. And also highlight that as a quantum computer maker, it's one thing to just go make qubits that you can initialize and set into different states and do readouts and so on. But to really make a quantum computer useful, you need all the layers of engineering that you do for traditional computation, right? So you need layers of software such as the low-level system operating system. You up to the top of the stack where you have a cloud user interface where programmers can upload programs and run them and get results. So we've invested a lot in all of that surrounding software and associated sort of environmental technology. I'll skip over some of this. I'll make the point here that like all the other vendors that you'll hear from today and in general, we're early on as an industry and we depend on each other and the ecosystem and a lot of partnerships to continue to further the research, to continue the development towards quantum advantage and commercially useful and basically civilizationally useful quantum computing. So this just highlights that we take that seriously and have numerous deep partnerships. Again, looking at the time here, I won't go into too much detail. I did mention earlier this idea of using quantum to enhance machine learning by either reducing the amount of data needed to train a model to a certain level of accuracy or to improve the accuracy given the amount of data that you have. And that is done by taking a traditional machine learning pipeline and transforming the data that you start with into a quantum space and manipulating it in a quantum mathematical way, and then using that quantum feature map to do the model training. And that's the simplest way to summarize the general approach to how quantum can improve machine learning. And I guess the last thing I'll say here is that it is possible for universities and smaller laboratories to jump into this game and get started. We have a 9-qubit QPU that lists for under $1 million. So with the other pieces, the dilution refrigerator and the control electronics that you would need, you can, for less than $2 million, get up and running with a superconducting quantum system and contribute to the research, do algorithm work, and start to prepare for that day, those coming days when quantum really will be revolutionizing many different use cases in many different industries. And just the final word is get involved today. It's happening now. It's super exciting. I can tell you, as an insider from a vendor, the customers and prospective laboratories and university folks that I deal with are doing amazing things out there, and it is the time to get involved and be part of it. So thanks again very much for having me, and I look forward to the fireside chat or panel, as it may be, in a few minutes. Thanks very much.
Thank you so much, Mr. Mike Piech, for sharing the Rigetti Computing Company's experience on the use of this superconducting computers. So at this point, we will be opening the floor for Q&A, and this will be facilitated by Mr. Andre Koenig. So may we request him to be here on stage, the chairman of One Quantum, CEO of Global Quantum Intelligence. Thank you so much, Mr. Andre.
Hey, Mike, how are you?
Hey, Andre, good to see you again.
Are you in New Jersey?
I am still in New Jersey, yes.
All right, so we'll need to send you off to bed soon, but first, quantum computer that we can actually see and touch. We talked about the theory this morning. Any questions from the audience? Otherwise, I'll go at it, but come on, you got a real quantum computer here. Mike, you're in business development. How do we sell these things? I was, you know my talks. I was a little critical about use cases and adoption this morning, which is still challenging sometimes, and the market for quantum isn't that big yet. Why should people get involved?
Yeah, so how do we sell them? A lot, the sales that have happened so far have been government laboratories and universities. So just, calling a spade, right? It's not like the big industrial customers are coming in and having these things fly off the shelves just yet. We're looking for that day, when the JP Morgan Chases and the Pfizers and the UPS or FedEx or DHL logistics companies are just dying to get more quantum compute for their respective areas. But really a lot of the systems that are being acquired now are for national government laboratories where the money is coming from a national initiative to catch up or have their scientists and their universities be leaders in the quantum game. And then again, some are universities where you've got a big enough, let's say, physics or computing or material science department with enough money to spend a few $1 million on a setup and a lab and get grad students working on actually contributing to the science of how do you make qubits and frankly to the software side of things of like, okay, what are the interesting algorithms? So that's a long-winded way of saying that a lot of the customers are research oriented, and it's buy a system to be part of it, right? But okay, why? As either a national government or as an academic institution, part of it is national pride, national security, future economic security. If you're a government, and if you're an academic institution, it's the same drive that drives the research of many other areas. It's the excitement, the challenge, and the opportunity to discover something and contribute something that makes people's lives better. So that's part of the why. There's a big passion factor among people who work at a company like Rigetti and people who buy systems from a company like Rigetti.
I want to see a line by the microphone. Come on, guys. But I'll ask one more question. Many things that make Rigetti unique. One of them is that you sell different QPUs. On your last slide, you had the 9 QPU version, of course, your newest one, and you have a very kind of detailed roadmap, and you're able to manufacture them, which is why you're doing this. What are these different evolutions of QPU best used for? What's your vision around this?
Yeah, I mean, one way to look at it is there's the 9-qubit is kind of the entry level, right? So our attempt to create to sort of take what's the easiest way to put this is that our fab is running new wafers all the time, right? We are constantly generating new test chips, and whole bunches of those chips get thrown away. I mean, essentially, they either they don't work or they're experiments that just sort of were dead ends, from a science or engineering standpoint. But there are a lot of good chips that come out of that otherwise wouldn't get used. And the original vision was, let's see if we can take some of those, and there are a lot more small qubit number chips that come out that are good that aren't otherwise going to get used than there are big chips. So we're like, okay, let's kind of kill two birds with one stone. Let's get some return on these, a little bit of money. Where they're not flying off the shelves, and we're not going to make huge margins on them. But it's an opportunity to sort of help stimulate the ecosystem and get some of the less well-funded labs or universities opportunities to get in the game. At the other end of the spectrum is, hey, the biggest, best, fastest, lowest error rate things we can possibly build at any given point in time. They're going to be the most expensive things, and they're going to be, what a big government budget that's trying to leapfrog to the front of the race is going to go after. And we have a couple of examples, like at the UK, where we put in 24 qubits last year and just upgraded them to 36 qubits. Budget and other reasons prevented them from going straight to the flagship 84 qubits. But that was still a kind of a deployment that was ultimately going to end up being toward the higher end of the product line there, as we'd say. But again, summarizing all that, I would say there's entry level, and then there's basically state of the art, the biggest and fastest thing that we can put out there. And occasionally somebody wants something in between.
Do we have time for one more question? I see one person at the mic. Beautiful audience question.
Hello. Hello.
Yeah.
So good afternoon. I'd like to ask if your company is purely focusing on the superconducting type of qubits or quantum computers, or have you been exploring like the topological or the optical or any other methods?
We are focused pretty much exclusively on superconducting. The other modes are different enough in both their science and their engineering. So, for example, the fab that we have set up, it would take a massive overhaul to make it useful in even partially helping create any of those other kinds of modalities. Unlike the software side of things, there's a huge capital expenditure that it takes to be able to fabricate the actual hardware, the chips and the surrounding hardware. And the modalities are so different that it's not really easy to sort of retool the plant from one approach to another. I mean, there are sort of families of related ones. So like the cat qubits or fluxonium. I mean, we could probably somewhat adapt our processes and capabilities to some of those adjacent kind of sister modalities, if you will. But to do any kind of like trapped ion or neutral atom or photonics would be just a total overhaul. So yeah, we are for the foreseeable future 100% transmon superconducting qubit focused.
Good. Thank you, Mike. Not sure if we're moving to the next. Yep.